Good day, hello and good day to Dr. Azma Hanim. My name is Ziad Ashraf, metric number 191588. So today I'm going to be talking about conduction and electron transport with my colleague and classmate Hamid Rastgoo. So next slide. Okay, so what's an electron band? An electron band is a band that surrounds an atom, and it consists of a large number of like not excited but electrons, right? So some of them are excited and some of them are not excited, right? So they are not ready for transport. So only the electrons on the outer bands, if it's filled or if there's only one electron, so that band is excited, right? And ready for transport of electrons. So each band contains 2 electrons per atom. And here we can see this is a band. The blue one is a band, and the red one is a band, but the gray one is an overlap, right? So I'm gonna come back to this graph later. Okay, so what's a conduct? A conduct is a transfer of something. So by transfer of something, we mean here, of course, it's a transfer of electrons. Actually, conduct is leading something. That's why they call them conductors, right? Conductors, they are, for example, the first atoms, or the, sorry, not atoms, the first electrons that transfer from an atom to another atom, right? So yeah, materials that transfer something through themselves. So we're gonna talk about the materials first, and then we go back to the graph. So these are 3 materials that conduct, and some of them don't conduct electricity, right? Are not good conductor of electricities. So there are insulators, semiconductors, and conductors. So the insulators, they don't have they don't conduct electricity because they're called insulators, right? They insulate the electricity instead. So they don't allow the passage of electricity through them. So if we attach 2 wires and I could an insulator in the middle, right? The electricity is not gonna go through, right? Because it's an insulator. It needs a huge amount of push or energy for that electricity to either go around or pass through, but I think we need too much energy to pass through an insulator. So yeah, that's what an insulator is. We're going to talk about conductors. So conductors allow electrons to flow through them easily, right? Because they don't have an energy gap, or what is it called here? A band gap. Yes, they don't have a band gap. Basically, the 2 bands are overlapping. That's why if even at room temperature, you can, if you give them a small push of energy, you can conduct something through them, like electricity or heat or something like that, right? Semiconductors actually lie in between insulators and conductors. So they exhibit both conducting and insulating at the same time. So you want a wire to be conductive when you give it energy at not at room temperature, specific temperatures. So we need to give it a little bit of a big push of electricity to conduct that electricity, or if it's heat, if it's a heat conduction experiment we're doing, we need to give it a little bit of a push because the energy gap isn't like an energy gap in between, right? A band gap. Here we can see the energy. So the energy is coming from the red part, the red bands, to the blue bands, right? So this is a metal or a conductor, a good conductor of energy, because here we have increasing energy, right? We don't have either heat or electricity. So yeah, here, these are overlapping, right? That's why they are good conductors, because we don't have to give them too much energy. Only a little bit of energy or a touch of energy, and then the electrons can go through the red part to the blue part. And here, these are the semiconductors, which we can start seeing a little bit of a gap in between, a band gap. So this band gap, there are Like the electrons are banned to be there, so they have to be either here or here. So we need to push the electrons from here to here, right? So we need to give them a little bit of a push of energy to conduct them or to push them to the conduction band. And these are insulators. So insulators have a bigger band gap than other materials. Their band gap is too big for energy to even go through, or we need too much energy to conduct electrons from the valence gap to conduction band. Sorry, valence band to conduction band. And so yeah, that's all from me. I'll leave the rest to my colleague Hamid. Thank you so much.
Hello, Doctor. Hello, everyone. So I'll be taking it from this point on, and I'm going to be talking about electron transport. So just to start it off, electron flow is possible because electrons can be freed from the electrostatic attraction to the proton of an atom's nucleus. So this is actually something we've learned back in chemistry in high school. Naturally, the electron that resides in the outer realm of an atom, which has the furthest distance from the core, which has the proton and neutron in it, is called the outer realm. And that is actually something that is called a valence electron, as you can see in the bottom right corner there. So how can this electron be freed? Well, there are multiple ways. If we add an amount of energy to it, this electron can actually be excited enough to be free. One of the ways of doing that is actually, you can see here, we're using heat, light, magnetism, and even electricity. So now we go a little bit deeper and see how insulators, semiconductors, and conductors use this freedom of electricity so that they can be conducted. So now we start off with insulators. Intriguingly enough, if we look back at our atom and we remember that this one single electron that's on the outer rim of an atom or of an atom's orbit is known as a valence electron. So this valence electron is actually stated in something called a valence band. So this is very intricate to our part, as we're going to discuss what happens when a material is being conducted or when we're giving energy to it. So if we look at here, we have something of a graph kind where we have a valence band where the valence electron resides in there. And then we have something called a gap from the valence band to the conduction band. So the whole point of making any material conductive is to get that electron, which is the valence electron, to go from a valence band to a conduction band. If we're able to achieve this, then that material can be conductive. Very simple. But as we know, insulators, and as they resist electron, as they resist conductivity, there's a bit of difficulty there. So what does give insulators their criteria and their characteristics? So as we can see here, there's something called a forbidden energy gap here in the middle between valence band and conduction band. This is called a forbidden energy gap because actually no electron is allowed to be there. Basically, all electrons are forbidden to stay in that gap. So they can either be in the valence band or in the conduction band. They cannot be in the space between. This is what's called a forbidden energy gap. So how can we get this electron, which is a valence electron, to go from a valence band to a conduction band with there being a gap in between? One of the methods, as we discussed, is that we can excite the electron to go from a valence band to a conduction, which means we have to give it energy, we have to give it heat, we have to give it either electricity or do other methods. So the problem with insulators is we're going to find out that if the electron is supplied with high energy, it can definitely jump across the forbidden gap. So it is possible for insulators to be conductive, but how much energy do we actually have to give them for this to be possible? So when the temperature is increased, some electrons will move to the conduction band. As we discussed, they will move from the valence band to the conduction band. This is why certain materials are insulators at room temperature and become conductors at high temperature. So it's very much in the realm of possibility for insulators to be conductive as well. How do we achieve that? So the resistivity of insulators lies approximately between 10 to the power of 11 and 10 to the power of 16 ohm meters. So that is a very huge number. And you can see there's a lot of resistivity that relies in insulators. That means if you really want to make them conductive, we have to give them a lot of energy. The energy has to exceed this amount of resistance. So with this, we're going to move on to semiconductors. With the explanation of insulators and the forbidden energy gap, there is actually something called a forbidden energy gap in semiconductors as well. But as you can see from the graph, it's actually much smaller than insulators. And that is the key point here. Because there's a small forbidden energy gap between a valence band and a conduction band, this allows us to play with that valence electron so that we can somehow give it enough energy to go from that valence band to the conduction band. The only difference between semiconductors and insulators is that we can accomplish this with less energy. So for instance, if we give a semiconductor a little bit of heat, or if we increase the temperature, the forbidden energy gap actually decreases, which means the distance between the valence band and the conduction band actually decreases and they get closer to each other. And with that said, we can easily transfer that valence electron from the valence band to the conduction band because the gap is just so minimal. With little amount of energy and little amount of effort, we can definitely get that energy, that electron to the conduction band. Thus, they become semiconductors. So semiconductors resistivity lies roughly around 10 to the power of 3 ohm centimeters. So already we can see a huge difference between semiconductors and insulators. Insulators were roughly around 10 to the power of 11 ohm meters. These are 10 to the power of 3 ohm centimeters. Now these are not exact numbers, but this is just a rough estimate. Naturally, different materials will have different values. So as we can see also from the graph in this bottom below, is that as the resistivity decreases, the temperature also increases. So by increasing temperature or by giving it energy or heat, the resistivity actually declines. It's a very sensible graph that defines semiconductors. So of course, famous examples are silicon and germanium, and it comes to no surprise that they're both from group 4 of the periodic table. This is all a great callback to chemistry when we had back in high school and in college. If you remember the periodic table, the group 4 has a huge amount of significance, specifically with conductivity. And we can see these examples with their figures as well. So now we finally move on to conductors. Now, there's a little bit of tricky here. Of course, metals are the best conductors, but metals actually, they separate into 2 different groups as well. Ones that are partially filled bands and one that are overlapping bands. So without wasting too much time, I'm just going to go deep into both of these categories and see what's the main difference between a partially filled band and an overlapping band. So right off the bat, you can see here that from this graph, you can see that there's actually no gap between the valence band and the conduction band. And you're right. There's actually no forbidden gaps in conductors. That's what makes them so perfect and great at conductivity. Because there's no gap anymore, the electrons can just freely move from the valence band to the conduction band. So what's the difference between a partially filled band and a overlapping band? So in conductors, the conduction band is the same as the valence band. As we said, because they're so close to each other and there is no forbidden gap, they basically become one single band. Now, we don't want to disinclude valence and conduction band. That's why we just call them that they're both in sync with each other. We definitely identify and acknowledge the valence and conduction band, but in some ways they're both in the same kind of band. With that said, some metals just have a partially filled valence band, and which means electrons can move freely without gaining extra energy, which means that even in room temperature, these electrons can easily go from the valence band to the conduction band and thus make the material conductive. Many of the metals that we know have this kind of priorities. So when we look at overlap bands, in some metals, the conduction band and valence band actually may overlap. What does this mean? The conduction band is occupied by many conduction electrons, causing them to become good conductors of electricity. For instance, in this picture, you can see there's actually very low, not a huge overlap, but there's definitely overlap between the valence band and the conduction band. So with the overlapping of the valence and conduction band, a very low potential difference can cause the continuous flow of current. Because these two bands overlap, that means we can just have a continuous flow of electrons coming and going, which gives us almost continuous conductivity, which that criteria alone sets apart an overlap band with a partially filled band. But at the end of the day, when we look at conductors such as metals, whether they're partially filled or overlapped, they're very conductive, and they cannot be compared in their conductivity with semiconductors and insulators. They are truly much more conductive uh, compared to semiconductors and insulators. So in the end, just to recap, we have metals where we have either a partially filled band, which is the on the left side, and on the right side we have an overlap between the empty and filled states. Then we have semiconductors, which is a very small gap between the uh, filled states and then the empty states. Basically, the empty representing the conduction band and then the overlap band. And then finally, we have insulators, where we have a huge gap and a large gap between the filled state and the empty state, representing the conduction band and the valence band. And that's a very brief introduction to valence band. This is how we can compare and distinguish between insulators, semiconductors, and conductors. This gives us a very great overview of what happens when we actually charge up any material to become conductive. Metals, of course, being conductive, they can be conductive in room temperature. For semiconductors, we might have to increase the temperature a little bit to achieve conductivity. And with insulators, we have to put in a lot of effort so that they can be conductive. And in many ways, we don't want insulators to be conductive conductors so that we can actually use them to resist against conductivity. In many cases, we either use rubber gloves so that we want to resist conductivity. But again, due to their constraints and characteristics, we use them at different situations. And with that said, we would like to thank you for listening. I hope this was intuitive. Thank you, Doctor.